This is the Chapter 5, Section 4, Skill 3, Example 2 from the notes. And it's another story problem that came from the AP free response section of an exam. This one was in 2009. And we're dealing with the rate at which the distance between the edge of a road and the edge of water is changing during a storm. So if we read this, we get information about the rate at which the distance between the road and the edge of the water is changing. That's given to us as an f of t, and that's going to be the derivative of some distance function with respect to time. And it's measured in meters per hour. So we've got this f of t, and its input is going to be hours. We are also told that the edge of the water was 35 meters from the road when the storm began. So that means we know the distance at time 0 is 35. Now, since we've studied our fundamental theorem of calculus and we know a derivative and we know a point on the original, we can now write the distance between the beach and the road at any time as the original distance plus the accumulation from 0 to t on that rate function, which is f. So if we look at part A, the question is, what was the distance between the road and the edge of the water? So we're looking for an output of this distance function at the end of the storm. Well, the storm lasted 5 hours, so I can input 5 into this function and then accumulate from 0 to 5 on that f, and I'd get my answer. So we'll go to the calculator in a second and do it all at the same time. Part B says, using correct units, interpret the value of f prime of 4. So that means I need to look at f prime and plug in that 4. And they told us that it was 1.007. And we want to talk about the units. So if we look up here at f prime is going to be a slope, which will be a meters per hour divided by hours. So that will be meters per hour squared. So that's going to represent the rate at which the f of t, which is the rate, in the distance between the beach and the road is changing at 4 hours. Well, maybe we should say 4 hours after the storm starts. So another way we could think about it is, since that's a positive number, that means the rate at which we are decreasing distance is a 1.007. If we look at part C, if we look at part C, it says, at what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? So to decrease most rapidly, that means we need to maximize or minimize the f of t. So we know that happens at endpoints or at critical points. This occurs when f prime of t equals 0 or undefined, or at endpoints. So that means we're going to need to graph f prime and find its zeros, and then we'll need to test each of those zeros in the rate function along with the endpoint. So we've got a 0, we've got a 5, and then we've got whatever critical points we find. So let's think about going to our calculators now so that we can work with it all. So we know that f is this function and f prime is this function, so I have put f in y1 and I've put f prime in y2. So if we look at part A first, that is going to be 35 plus the accumulation from 0 to 5 on f. So on my home screen I will do 35 plus the accumulation of y1 of x with respect to x from 0 to 5. And that gives me 26.495 meters. That's the distance between the beach and the road. If we look at C, we want to maximize or minimize the f function, which means we need to be looking at the graph of y2. So I'm going to turn off y1, and I'm going to set my window to 0 to 5. And I'm interested in when it crosses the x-axis, so we could probably just look from -1 to 1 and still see it. So if I graph that now, we can see that I'm going to hit a max here, and I'm going to hit a min here. And I can find both of those locations by looking for the zeros. Lower bound, upper bound. I get one of them is 0.662. Notice that that's stored as an XC, so I can plug that into F right now before I go find the other. So I'm going to go to my home screen. Remember, F is in Y1, so I can do Y1 of 0. That gives me a -2. I can do Y1 of that X alpha C. That gives me my next output. I can now go back to my graph and look for my second 0. I'm already to the left, so I've already got my lower bound. Upper bound is probably 4. And I've got another 0 that's now 2.840. I'm going to store that as XC, and on the home screen I can do Y1 of XC again. This time I'll get a -2.2696, and then I need F of 5, which is Y1 of 5. I end up, oops, diamond enter, end up with a -0.480. Now I'm interested in at what time during the 5 hours was the distance decreasing most rapidly. So decreasing means we need the most negative. That's going to occur here. So we would write at t equals 2.840 hours, the distance between the road and the edge of the water was decreasing most rapidly. Okay, last part. D says, after the storm, a machine pumped sand back onto the beach so that the distance between the road and the edge of the water was growing at a rate of G of P meters per day, where P is the number of days since the pumping began. I want to write an equation involving an integral expression whose solution would give the number of days that sand must be pumped to restore the original distance. Okay, so we got to think about the original distance and how much we lost in that 5-day storm. So part D, at some point we're going to be dealing with how much we lost, which is the accumulation of F from 0 to 5. So this is going to be what we lose, so that's going to be a negative impact on the distance. So we would need the opposite of that to be what we accumulate with this G. So we're going to go from 0 up to another day, X on G of P with respect to P. So if I accumulate the rate at which I'm pumping things back from the time 0 up to X, so that's how many days I'm going to be pumping sand back on, I need that accumulation, which will be the number of meters, to equal the opposite of the meters that we lost.